At 3:17 in the morning, the alarm went off inside the Space Weather Prediction Center in Boulder, Colorado. Not a beep, not a notification on someone's phone. The automated monitoring system that watches the sun around the clock every day, every year, without pause, triggered a threshold alert that the duty forecaster on shift had seen only once before in their career. The alert said G5. Most people have never heard of the G scale. Most people do not know that the National Oceanic and Atmospheric Administration maintains a 5-level geomagnetic storm classification system that runs from G1, a minor event that barely registers outside the research community, up through G5, an extreme event that the agency defines in precise clinical language as capable of widespread voltage control problems, some protective systems incorrectly tripping out key assets from the power grid, and complete radio blackout on the entire sunlit side of the Earth. G5 means the most extreme category of geomagnetic disturbance on the planet's official scale. G5 means the planet's magnetic field is being compressed and twisted by a wave of charged particles moving faster than 3 million kilometers per hour. G5 means that every transformer, every power line, every satellite, every GPS receiver, every undersea internet cable, every pipeline, and every aircraft currently in flight is operating inside an electromagnetic environment that was not present when the engineers who built those systems ran their design calculations. The last time the NOAA Space Weather Prediction Center issued a G5 alert was in May of 2024. The most powerful geomagnetic storm in 20 years, an event that produced auroras visible from Florida and Texas, that disrupted agricultural GPS equipment across the American Midwest during the critical spring planting season, and that caused SpaceX to take emergency measures to protect its Starlink satellite constellation from the increased atmospheric drag produced when the storm heats and expands the upper atmosphere. That event registered a KP index of 9, the maximum on the planetary scale. The event currently heading toward Earth is different, not because the classification says G5. The May 2024 event said G5 as well. This event is different because of what the Parker Solar Probe detected in the solar corona in the 72 hours before the eruption. Because of what the DSCOVR satellite at the L1 Lagrange point is measuring in the arriving solar wind right now. Because of the specific orientation of the magnetic field embedded in the approaching cloud of plasma, an orientation that the researchers who study geomagnetic storm impacts have been quietly describing in their technical papers and in their conference presentations as the scenario they most fear. We are going to explain all of that. We are going to explain it in the kind of detail that allows you to understand not just what is happening, but why it matters. Why a cloud of ionized particles traveling from a star 150 million kilometers away can, within hours of its arrival, begin shutting down the power grid of a continent. But first, let me tell you the number. The number that the Space Weather Prediction Center uses to describe the magnetic field orientation of an incoming coronal mass ejection is called the BZ component. It is a measure of whether the magnetic field in the arriving solar wind is pointing northward or southward relative to Earth's own magnetic field. When BZ is positive, when it points northward, it is roughly aligned with Earth's magnetic field. The two fields connect partially, and the storm's energy is deflected. Earth's magnetosphere absorbs some of the impact and distributes the energy through its normal channels. Auroras form at high latitudes. The KP index rises. If the event is strong enough, power companies in high-latitude regions take precautionary measures. But the planet's electromagnetic infrastructure survives largely intact. When BZ is strongly negative, when the solar wind's magnetic field points southward, it is anti-aligned with Earth's magnetic field. The two fields do not deflect each other, they reconnect. The solar wind punches through the magnetosphere's protective barrier. The storm's energy does not flow along the outer boundary of the magnetosphere. It flows inside. It flows into the magnetosphere's interior. It drives electrical currents in the ionosphere. Those currents induce voltage in long electrical conductors on the ground, power lines, pipelines, railway tracks, and the windings of large electrical transformers. The DSCOVR satellite is currently reading a BZ value of negative 45 nanoteslas. For context, the May 2024 event, at its most intense, produced a sustained BZ of negative 24 nanoteslas. The event heading toward Earth right now is carrying a southward magnetic field nearly twice as strong. We will come back to what negative 45 nanoteslas means for the grid. Because to understand that number in its full context, to understand why the researchers who read it at 3:17 a.m. in Boulder sat very quietly for a moment before reaching for the phone, you first need to understand what happened on a September morning in 1859, and why the world has been lucky for 165 years that it hasn't happened again. On the morning of September 1st, 1859, a British astronomer named Richard Carrington was doing what he did every morning. He was drawing the sun, not as a metaphor, literally drawing it, making detailed sketches of the sunspot groups visible on the solar disk through his telescope, recording their positions, their sizes, their shapes, the gradual evolution of their structure from day to day. This was routine solar observation work in the Victorian era. Carrington had been doing it for years. He was very good at it, and his meticulous records of sunspot activity would eventually contribute significantly to the understanding of the solar cycle. On the morning of September 1st, while sketching a particularly large and complex sunspot group in the northern hemisphere of the Sun, Carrington observed something that had never been documented before. A brilliant flash of white light erupted from within the sunspot group. A burst of intensity so sudden and so bright that it overwhelmed the contrast of his observation setup, which had been carefully calibrated for the moderate brightness of ordinary sunspot structures. The flash lasted approximately 5 minutes. Carrington noted the time and recorded what he had seen. He found a colleague, Richard Hodgson, who had independently observed the same event from a different location. The two men compared notes. They had no framework for understanding what they had witnessed, because no one had ever witnessed it before. They described it faithfully, published their observations, and noted that it was remarkable. 17 hours later, the world found out what it meant. In the early morning hours of September 2nd, 1859, telegraph systems across North America, Europe, and Australia failed simultaneously and spectacularly. Not in the ordinary way that telegraph systems sometimes failed, a broken line, a failed battery, a mechanical fault. The 1859 failure was different in character and in scale. Telegraph operators reported that their equipment was producing sparks and shocks from induced electrical currents so strong that the current no longer needed the batteries that were supposed to power the system. Some operators disconnected their batteries entirely and found that the telegraph could still transmit, powered entirely by the anomalous currents induced in the wires by the geomagnetic disturbance. Other systems failed because the induced currents exceeded what the equipment was designed to handle. paper tape caught fire at some stations, and at least one operator was thrown from his chair by an electrical shock delivered through the equipment he was working on. Auroras were visible across North America, as far south as Cuba and Hawaii. In the southern hemisphere, they appeared over Chile and Australia. People who had never seen the northern lights in their lives, who lived at latitudes where auroras were unknown, outside the experience of any living persons, stepped outside and watched the sky glow in red and green curtains of light that many of them found terrifying and unexplainable. The storm lasted approximately 18 hours. No one died directly from the storm itself. The technology of 1859 was simple and robust enough to survive. Telegraph systems were damaged and disrupted, but they were repaired. Compasses behaved erratically for a day. The auroras faded. The world went back to normal. The event was named the Carrington event, after the astronomer who observed the solar flare that preceded it. It was, by every measure that can be applied retroactively, the most powerful geomagnetic storm in recorded history. The event was named the Carrington event, after the astronomer who observed the solar flare that preceded it. It was, by every measure that can be applied retroactively, the most powerful geomagnetic storm in recorded history. But the Carrington event is not the only historical data point that informs our understanding of what a severe solar storm can do to modern infrastructure. There is a sequence of events spanning the 20th and 21st centuries that tells a story of escalating encounters between an increasingly electromagnetic civilization and a sun that has not changed its behavior at all. In May of 1921, a geomagnetic storm, now estimated at approximately Carrington intensity, struck the Earth. This event, called the New York Railroad Storm because of the damage it caused to telegraph and early railroad signal systems, produced fires in telegraph offices across North America and Europe. The transformer station at Brewster, New York, caught fire. Station buildings in Sweden burned. The induced currents in telegraph lines and early electrical systems caused the widespread disruption across a civilization that was just beginning to depend on electrical infrastructure. Had the 1921 event occurred in 2026, it would have encountered a planet with 10,000 active satellites, a global GPS system, undersea internet cables carrying 99% of international data traffic, and a power grid whose high-voltage transformers are essential nodes for the electricity supply of hundreds of millions of people. The 1989 Quebec event was the first modern demonstration of what a severe geomagnetic storm does to a sophisticated power grid. But the scientific data from that event, its Kp value of approximately 9, its DST of approximately -600 nanoteslas, its peak GIC measurements in the Hydro-Quebec system, established the reference point against which all subsequent events have been measured. The October 2003 Halloween storms produced two of the most intense solar flares ever recorded: an X-17 event on October 28th, and what is now estimated to have been an X-28 or larger event on November 4th. These flares produced radiation storms that forced the crew of the International Space Station to shelter in the more heavily shielded Zvezda service module. They caused satellite anomalies across multiple commercial and government fleets. They produced aurora visible from Texas and Florida. They triggered automatic protective disconnections in the Swedish power grid, causing a brief outage that affected 50,000 people in Malmö. The Halloween storms did not cause a major grid collapse. They came close enough to provide a significant data set for researchers studying grid vulnerability, and the analysis of that event contributed directly to the NERC geomagnetic disturbance standards issued in subsequent years. The most recent significant event before the current storm was the May 2024 geomagnetic storm, the one that produced G5 conditions for approximately 24 hours, drove aurora to low latitudes across both hemispheres, and caused the agricultural GPS disruptions that cost farmers across the American Midwest during the spring planting season. That event had a peak BZ of approximately -24 nanoteslas and a peak DST of approximately -412 nanoteslas. The current storm's second main phase BZ is -52 nanoteslas. Each of these historical events added to the database from which current infrastructure vulnerability assessments are built. Each one also demonstrated, to varying degrees, that the gap between scientific understanding of the hazard and operational readiness of critical infrastructure has not been fully closed. Scientists analyzing the chemical signature of the storm, preserved in ice cores from Greenland and Antarctica, have estimated its intensity at a DST index of approximately -850 nanoteslas. For comparison, the DST value of the May 2024 storm, the most powerful event in 20 years, reached approximately -412 nanoteslas. The Carrington event was more than twice as powerful as the strongest storm in the modern instrumental era. A study commissioned by Lloyd's of London in 2013 estimated the economic impact of a Carrington-scale event on the modern United States alone at between $0.6 and $2.6 trillion, with a wide range reflecting uncertainty about how many large power transformers would be permanently damaged. Large power transformers are the critical vulnerability. They are the reason this matters. A high-voltage power transformer is a device that weighs between 100 and 400 tons, costs between $3 and $10 million, takes 12 to 18 months to manufacture, and is built to order by a small number of specialized manufacturers worldwide. The United States has approximately 2,000 of these transformers in its high-voltage transmission grid. Most of them are more than 25 years old. None of them were designed to withstand the kind of geomagnetically induced currents that a Carrington-scale event would produce. When a geomagnetically induced current enters a transformer's windings, it does something that the transformer's cooling and insulation systems were not designed to handle. It saturates the transformer's core, the magnetic material that the transformer depends on to function efficiently. A saturated transformer generates enormous heat in its windings and core, far beyond the design limits of the cooling system. Over a period of minutes to hours, the insulation degrades, the transformer fails. Not a failure that can be reset by flipping a breaker. A catastrophic, permanent physical failure that requires the transformer to be removed, shipped to a manufacturer, rebuilt or replaced, and then reinstalled. The lead time for that process in the current manufacturing environment is measured in months to years. If the Carrington event happened today, multiple large transformers across the grid would fail simultaneously in the first hours of the storm. The grid would begin to fail. The cascade of failures, each one creating instability that overloads adjacent sections of the network, could extend the initial damage far beyond what the direct storm currents produced. The Quebec event of 1989 demonstrated a scaled-down version of exactly this sequence. Let me tell you what happened there, because it is the closest analogy the modern era has for what a severe geomagnetic storm does to a grid. On March 13, 1989, a geomagnetic storm measuring approximately G5 on the modern scale struck the Earth. The Hydro-Quebec power grid, which supplies electricity to the province of Quebec in Canada, collapsed in 92 seconds. The entire provincial grid, all of it simultaneously, went from normal operation to zero within a minute and a half. 6 million people lost power. The outage lasted 9 hours. The grid failed so fast that the automatic protective systems that were designed to prevent exactly this kind of cascade did not have time to respond meaningfully. The induced currents overwhelmed the grid's protective equipment faster than the equipment could operate. 9 hours without power for 6 million people. From a geomagnetic storm that, by the current analysis of historical records, was significantly less powerful than the Carrington event, and significantly less powerful than what the DSCOVR satellite is measuring in the solar wind right now. We will come back to Quebec, but first we need to understand the mechanism. The physics of how a cloud of plasma erupted from the surface of a star can, 150 million kilometers and a day or two later, cause a transformer in New Jersey to melt. Because once you understand the mechanism, the number from DSCOVR, -45 nanoteslas, stops being an abstract measurement. It becomes a description of something that is actively happening right now, 1.5 million kilometers from Earth, moving toward us at a speed that makes the word warning feel inadequate. The Sun is not a stable object. This is the foundational fact that most people's intuitive understanding of solar physics gets wrong. The Sun is a nuclear furnace 1.4 million kilometers in diameter, producing energy through the continuous fusion of hydrogen into helium in its core. It is, in human terms, extraordinarily powerful and extraordinarily ancient, approximately 4.6 billion years old, roughly halfway through its main sequence lifetime, but stable it is not. The Sun's surface, the photosphere, is a constantly churning, roiling plasma at a temperature of approximately 5,500 degrees Celsius. Above the photosphere, counterintuitively, the temperature rises rather than falling. The solar corona, the outermost layer of the Sun's atmosphere, reaches temperatures of 1 to 3 million degrees, hundreds of times hotter than the visible surface below it. The mechanism that heats the corona to these extreme temperatures is still not fully understood and remains one of the major open questions in astrophysics. The corona is also the origin of the solar wind, a continuous stream of charged particles, predominantly protons and electrons, that flows outward from the Sun in all directions at speeds of 300 to 700 kilometers per second. The solar wind permeates the entire solar system. Earth moves through it continuously. Earth's magnetic field deflects it. The magnetosphere is, in essence, a bubble of protected space carved out of the solar wind by the planet's magnetic field. Without the magnetosphere, the solar wind would strip away the atmosphere. It would sterilize the surface. It has done exactly this to Mars, which lost its global magnetic field billions of years ago and has been gradually losing its atmosphere to the solar wind ever since. Earth's magnetosphere is the reason complex life exists on this planet. That is the background state, the ordinary continuous solar wind that Earth has been navigating for 4.5 billion years. The coronal mass ejection is different. A coronal mass ejection, a CME, is an episodic eruption of plasma and magnetic field from the Sun's corona. It is not a continuous flow. It is a discrete event, a bubble, sometimes containing billions of tons of plasma, launched from the Sun's surface when the complex magnetic field structures in the corona become unstable and reconnect violently, releasing stored magnetic energy in a burst that accelerates plasma to speeds of 500 to 3,000 kilometers per second. The fastest CMEs cover the 150 million kilometers from the Sun to Earth in under 24 hours. The slower ones take 3 to 4 days. The average transit time is approximately 2 to 3 days. The critical variable is not the speed. Speed determines when the storm arrives, but not how severe it is. The critical variable is the magnetic field orientation within the CME. The BZ component we discussed in the first act. The critical variable is not the speed. Speed determines when the storm arrives, but not how severe it is. The critical variable is the magnetic field orientation within the CME, the BZ component we discussed in the first act. Before we examine what BZ does to Earth's magnetosphere, there is context about the current moment in the solar cycle that makes the timing of this event more significant than it might otherwise appear. The Sun follows an approximately 11-year cycle of activity measured by the rise and fall of sunspot numbers. At solar minimum, the Sun has few sunspots, produces few flares, and launches fewer CMEs. At solar maximum, sunspot numbers peak, active regions proliferate on the solar disk, and the frequency and intensity of solar energetic events increases substantially. Solar Cycle 25, which began in December 2019, has been significantly more active than the previous cycle, Solar Cycle 24, which was one of the weakest cycles in a century. The solar physics community had predicted a moderate Solar Cycle 25. The Sun delivered a notably stronger one. The peak of Solar Cycle 25, solar maximum, was projected to occur around 2025 and has been producing elevated activity throughout 2024 and 2026. The active region that produced the current CME eruption has been among the largest complex sunspot groups observed during this cycle, with a magnetic complexity classification of beta gamma delta, the highest classification on the NOAA sunspot magnetic complexity scale, indicating the presence of multiple polarity inversion lines within a single active region and the highest probability of producing major flare activity. Active regions with beta-gamma delta classification are responsible for the majority of X-class solar flares and major CME eruptions in the historical record. They are the configurations that produce the events that end up in the history books. The current active region has been visible on the solar disk for approximately 10 days as it rotated with the Sun. In those 10 days, it produced 4 M-class flares and 1 X-class flare before the major eruption that launched the current CME. Each of the preceding flares represented a partial energy release from the complex magnetic structure. They did not fully discharge the stored energy. The magnetic topology continued evolving, becoming more complex and more unstable until the primary eruption. The solar physics community has been watching this active region with particular attention for the last week, precisely because of its unusual size and magnetic complexity. The Parker Solar Probe's close approach pass in the 48 hours before the eruption was not scheduled in response to the region's activity. It was a planned scientific pass that happened to coincide with the region's most active period. The quality of the data produced by that coincidence has provided an unprecedented look at the pre-eruptive configuration from a distance previously unachieved by any spacecraft. Understanding the solar cycle context matters because we are currently in a period of elevated CME production frequency. The probability of additional major events over the next 12 to 24 months, while the Sun remains near its cycle maximum, is higher than it will be in 3 to 5 years when the Sun approaches the next minimum. The current event is not an isolated anomaly in an otherwise quiet Sun. It is one of the larger events in an active period. Here is why BZ matters at a physical level. Earth's magnetic field at the magnetopause, the outer boundary of the magnetosphere, approximately 70,000 kilometers above the dayside surface, points predominantly northward. When the solar wind's embedded magnetic field also points northward, the two fields are aligned. Aligned fields do not reconnect easily. The solar wind is partially deflected. The magnetosphere compresses and distorts, but maintains its essential structure. The storm's energy flows around the magnetosphere more than through it. When the CME's magnetic field points southward, when BZ is negative, the opposite occurs. An anti-parallel magnetic field configuration is unstable. The two fields reconnect at the dayside magnetopause in a process called magnetic reconnection. The reconnected field lines sweep around to the night side of the planet, creating an entry channel for solar wind energy into the magnetosphere's interior. Charged particles stream in along the reconnected field lines. Electrical currents are driven through the ionosphere. The ring current, a band of trapped charged particles circling Earth at altitudes of several Earth radii, intensifies. It is the intensification of the ring current that produces the geomagnetic disturbance at the surface. The ring current acts like an enormous electromagnet encircling the planet. When it intensifies, it partially cancels Earth's own magnetic field, reducing the field strength measured at the surface. This reduction is what the DST index measures. The more negative the DST, the more intense the storm, the stronger the ring current, the more energy the magnetosphere has absorbed. The intensified ring current also produces the geomagnetically induced currents, the GICs, that damage transformers and pipelines. Long conductive structures on the ground act as antennas for the changing magnetic field. Faraday's law of electromagnetic induction states that a changing magnetic field induces a voltage in any conductor it passes through. The more rapidly and more severely the magnetic field changes, the larger the induced voltage. The rate of change of Earth's magnetic field during a severe geomagnetic storm is extraordinary by any engineering standard. Rates of several hundred nanoteslas per minute have been recorded during historical storms. The transformers and pipelines that were engineered and installed over the last century were designed for an electromagnetic environment where the background field changes slowly and predictably. They were not designed for an environment where the field is being violently compressed and twisted by an external source, delivering a BZ of -45 nanoteslas. This is not a theoretical vulnerability that might manifest if conditions align perfectly. It is a documented physical mechanism with a documented historical precedent, Quebec 1989, with its 92-second collapse, showing what it does to infrastructure when conditions align. There is one more component of the mechanism that is critical to understand: the storm sudden commencement and the subsequent main phase. A CME arrival at Earth is not a single event. It has a structure. The CME is preceded by a sheath region, the compressed solar wind piled up ahead of the fast-moving CME. The sheath arrives first and produces an initial disturbance, typically a brief intensification of the geomagnetic field, followed by a rapid decrease. This is the storm's sudden commencement. It is detectable everywhere on Earth simultaneously. After the sheath comes the main body of the CME, the magnetic cloud, the billion-ton bubble of plasma with its embedded southward magnetic field. When this arrives and the southward BZ engages with Earth's magnetosphere, the main phase of the storm begins. This is when the DST index drops to its minimum. This is when the GICs reach their maximum intensity. This is when transformers are at their highest risk. The main phase can last hours. During the main phase, the geomagnetically induced currents are not steady. They fluctuate as the magnetosphere responds dynamically to the varying solar wind conditions. The most dangerous moments are the periods of most rapid magnetic field variation, the sudden intensifications and relaxations that occur as reconnection proceeds on the day side and magnetic flux is transported to the night side. The DSCOVR satellite, sitting at the L1 Lagrange point, 1.5 million kilometers sunward of Earth, is measuring the approaching CME's properties right now. It is measuring the solar wind speed, the proton density, and most critically, the magnetic field vector, including the BZ component. The reading is -45 nanoteslas, and it has been sustained for the last 2 hours. It is not fluctuating toward zero. It is not trending toward recovery. The southward field has been steady and strong since the CME's magnetic cloud made contact with the L1 point. At the solar wind speed currently being measured, approximately 2,200 kilometers per second, the distance from L1 to Earth represents approximately 11 minutes of transit time. The main phase of this storm began approximately 20 minutes ago. In the entire history of human civilization's attempt to build warning systems designed to give people time to respond to incoming threats, there may be no system with a more inadequate lead time than the one we currently operate for solar storm warnings. The DSCOVR satellite, positioned at the L1 Lagrange point, is the primary sentinel for incoming space weather events. L1 is a gravitational balance point between the Earth and the Sun, where an object can maintain a stable position with minimal station-keeping fuel. It sits approximately 1.5 million kilometers from Earth, about 1% of the total Earth-Sun distance. When a CME arrives at L1, it has between 15 and 60 minutes of travel time remaining before it hits Earth's magnetosphere. The exact lead time depends on the CME's speed. Fast CMEs, the dangerous ones, the ones moving at 2,000 to 3,000 kilometers per second, provide approximately 15 minutes of warning after their arrival at DSCOVR. 15 minutes. That is the window between confirmation that a severe geomagnetic storm is imminent and the storm's arrival. Not 48 hours, like a hurricane forecast. Not 72 hours, like a major flood warning. Not the days of preparation time that advanced earthquake scenarios allow for. 15 minutes. Power grid operators in high-latitude regions, Canada, Scandinavia, the northern United States, have protocols for responding to space weather alerts. The protocols involve reducing the loading on transmission lines, temporarily disconnecting certain types of equipment that are particularly vulnerable to geomagnetically induced currents, and alerting control room operators to watch for abnormal readings. Executing those protocols fully and safely under normal conditions takes approximately 15 to 30 minutes. With 15 minutes of warning after DSCOVR detection, the window for executing protective measures is essentially zero. The NOAA Space Weather Prediction Center issues forecasts for space weather events in the same way that meteorologists issue hurricane or tornado forecasts, using models of solar activity, solar wind propagation, and magnetospheric response to project what is likely to happen and when. The center issues alerts, watches, and warnings across a spectrum of space weather phenomena, including solar flares, radiation storms, and geomagnetic storms. These forecasts can provide days of advance notice when the sun produces a large solar flare and the associated CME. The transit time from Sun to Earth for even the fastest CMEs is measured in hours. If a major X-class flare is observed on the Sun and a CME is confirmed, the forecasters can provide 24 to 48 hours of warning that a geomagnetic storm is coming, with probabilistic guidance on its likely severity. What the forecasters cannot tell you until the CME arrives at L1 is the one number that determines everything, the BZ component. The BZ value of a CME cannot be reliably predicted from remote solar observations. It depends on the internal magnetic structure of the ejected plasma, a structure that is shaped by the complex magnetic topology of the corona at the time of eruption, modified by the dynamics of the eruption itself, and further altered during the CME's transit through interplanetary space. The physics is understood in principle, but the specific BZ value of any particular CME cannot be computed from the initial conditions of the eruption with current models. It can only be measured. And it can only be measured when the CME arrives at a point close enough to Earth to provide useful warning time. The L1 point is that measurement location. DSCOVR is that instrument. And the measurement, when it is positive, means the storm may be manageable. When it is negative 45 nanoteslas and sustained for 2 hours, it means what it means. The scientists and engineers who work in space weather prediction and impact assessment have been making the argument for years in technical reports, in government briefings, in academic papers and trade publications that the 15-minute warning from L1 is insufficient for critical infrastructure protection. They have proposed placing additional monitoring spacecraft further from Earth at the L5 point, which lags Earth in its orbit by 60 degrees, or in solar orbit at distances that would provide hours of additional warning time. These proposals have been discussed, studied, and partially funded. No dedicated L5 space weather mission has yet been launched by either the United States or the European Space Agency, though planning and development work is ongoing. In the meantime, the operational warning system is what it is. L1, DSCOVR, 15 minutes. The storm heading toward Earth has been traveling through interplanetary space for approximately 28 hours since the coronal mass ejection was first confirmed on the solar disk. For 27 hours and 45 minutes of that transit, the BZ value was unknown. 15 minutes ago it became known. Negative 45 nanoteslas. The grid operators who received the alert from SWPC at 3:17 a.m. are implementing what they can implement in the time available. Some protective measures are being taken. Some equipment is being switched to safer configurations. The most vulnerable large transformers in high-latitude regions are being identified and monitored. But the 15-minute window does not allow for the full execution of protective protocols across an interconnected grid serving hundreds of millions of people. We are in the main phase of the storm now, and there is something that has not yet been publicly discussed that we need to address directly. The Parker Solar Probe, NASA's spacecraft that has been making close approach passes of the Sun, getting closer to the solar surface than any previous human-made object, made a pass within 6 million kilometers of the Sun's surface in the 48 hours before this CME erupted. The data from that pass, transmitted back to Earth in the hours after the eruption, showed something in the pre-eruptive magnetic field configuration that the solar physics team flagged immediately. We are going to cover what they found, but to understand what it means, we first need to look at the specific numbers on the grid right now, because the numbers are changing. And the direction they are changing is not the direction the system was designed to accommodate. On March 13, 1989, the Hydro-Quebec power grid collapsed in 92 seconds. Let me take you through those 92 seconds. At 2:44 a.m. local time, a series of geomagnetically induced current surges began entering the Hydro-Quebec transmission system through its grounded neutral connections, the points where the grid's high-voltage lines connect to Earth through the grounding infrastructure. These currents were not generated by any source within the grid. They came from the changing magnetic field produced by the geomagnetic storm. The currents entered the windings of the large static VR compensators, reactive power compensation devices that help maintain the voltage stability of the long transmission lines that carry power from the James Bay hydroelectric stations, northern Quebec, to the load centers in the south. The compensators are sensitive to the kind of harmonic distortion that geomagnetically induced currents produce in transformer cores. 5 of them tripped off in rapid succession within the first minute. With 5 compensators offline, the reactive power support for the long transmission lines was suddenly insufficient. The voltage on the lines began to oscillate. The protective relays on several high-voltage transmission lines detected the oscillation and interpreted it as a fault condition. They tripped the lines. With the lines tripped, the generation-to-load balance in the southern part of the province collapsed. The frequency of the AC current, which must be maintained at precisely 60 cycles per second for the grid to function correctly, deviated outside the acceptable range. The remaining generators in the affected area detected the frequency deviation and automatically disconnected to protect themselves from damage. The cascade ran its course in 92 seconds. The entire provincial grid went from normal operation to zero. 6 million people. 9 hours in the dark. The event left permanent damage in its wake. A large step-up transformer at the Chibougamau substation was severely damaged by thermal stress from GIC-induced heating in its windings and had to be taken out of service for repair. The repair took weeks. That was the Quebec 1989 event, which is currently estimated to have produced peak GIC levels in the range of hundreds of amperes in some parts of the Hydro-Quebec system. The event currently underway is producing a sustained southward BZ of -45 nanoteslas. The Quebec event is estimated to have produced a BZ of approximately -35 nanoteslas at its peak. The implications of this comparison are not subtle. The geomagnetically induced current that flows in a grounded conductor on Earth's surface scales with the rate of change of the horizontal component of the magnetic field. The rate of change, in turn, scales with the intensity of the driving Bs. A storm with a sustained Bs of -45 is not producing GICs that are 29% larger than the Quebec event's GICs. The relationship is not linear. The magnetospheric response to stronger driving is nonlinear. The GIC levels in a storm of this intensity would be substantially larger than what Quebec experienced. Power grid operators in North America are aware of this. The North American Electric Reliability Corporation, NERC, has issued geomagnetic disturbance standards that require transmission asset owners to assess their grid's vulnerability to geomagnetically induced currents and to implement mitigation measures for high-impact, low-frequency events. The implementation of those standards has been ongoing since 2016. The process of identifying vulnerable transformers, installing GIC monitoring systems, and deploying GIC blocking devices, hardware that prevents the low-frequency induced currents from entering transformer windings, has been progressing across the industry. Not every vulnerable transformer has been mitigated. The most conservative estimates of the number of large high-voltage transformers in North America that remain unprotected against severe GIC events run into the dozens to hundreds, depending on the definition of severe and the specific vulnerability assessment methodology used. At current manufacturing capacity and supply chain conditions, replacing a severely damaged extra high-voltage transformer takes between 12 and 24 months if the specific model required is not in stock, and 6 to 12 months if a suitable replacement unit is available. There are currently no significant stockpiles of spare EHV transformers in North America. In 2008, Congress passed the SHIELD Act as part of broader grid security legislation, directing the Department of Energy to evaluate and address transformer spare inventory vulnerabilities. The Department of Energy has conducted studies. The electric industry has developed an agreement for transformer sharing, the Recovery Transformer Program, that establishes protocols for companies to share spare units in the event of a large-scale failure. The Recovery Transformer Program is designed around scenarios involving a small number of transformer failures in a geographically concentrated area. A severe geomagnetic storm does not produce transformer failures in a geographically concentrated area. It produces transformer stress across the entire high-latitude transmission network simultaneously because the geomagnetically induced currents affect every grounded conductor on the same hemisphere of the planet at the same time. The Recovery Transformer Program's sharing protocols were not designed for this scenario. The Recovery Transformer Program's sharing protocols were not designed for this scenario. There is a specific economic analysis underlying the gap between the known vulnerability and the incomplete mitigation, and it is worth understanding because it explains why a hazard that has been clearly documented for more than 30 years has not been fully addressed. The cost of retrofitting the most vulnerable large transformers in the North American grid with GIC blocking devices, neutral blocking capacitors, which prevent the low-frequency geomagnetically induced currents from entering transformer windings while allowing the normal AC power currents to pass, has been estimated at approximately $100 to $200 million for the highest priority assets. This is not a trivial sum, but it is modest compared to the economic impact of a major grid failure event. The problem is the structure of the incentive. The electric utility industry is regulated on a cost-of-service basis in most jurisdictions. Utilities recover their costs by including them in the rates charged to customers, subject to approval by state and federal regulators. Investing in protection against a low-probability, high-consequence event requires regulators to approve rate increases to fund the protection. Regulators, who are accountable to customers who experience rate increases immediately and catastrophic grid failures only rarely, face institutional pressure to scrutinize protective investments carefully. The standard for approving investments in low-probability risk mitigation requires a probabilistic cost-benefit analysis. The probability of a Carrington-scale event in any given year is estimated at approximately 1 to 2% based on the historical record. The annual probability is low, even though the multi-decade probability is significant. A 1 to 2% annual probability multiplied by a several trillion-dollar consequence produces an expected annual cost that justifies substantial preventive investment. But the expected value calculation requires accepting the probability estimate, which depends on a historical record that contains only a handful of events in the observational era, and accepting the consequence estimate, which carries wide uncertainty bounds. In a regulatory environment focused on near-term cost recovery, the investment that would prevent a once-in-several-decades catastrophe can be difficult to approve and fund. This is not a uniquely American problem. The same regulatory structure and the same economic incentive challenges exist in most developed world power systems. The UK, which commissioned the Lloyd's study that produced the $0.6 to $2.6 trillion US damage estimate, has conducted extensive space weather impact assessments for its own grid and has made more progress on protective investment than some other jurisdictions. The Nordic countries, which are at high latitudes and therefore face the highest GIC intensity in severe storms, have also made significant investments in protective monitoring and mitigation. But the global grid as a whole, the sum of all the high-voltage transmission infrastructure that serves the world's population, remains incompletely protected against the scenario that is currently unfolding. None of this means catastrophe is inevitable. The protective measures that have been implemented since the Quebec event, ground resistance improvements, some GIC blocking devices, operational procedures for reducing grid loading during storm events, reduce the vulnerability compared to what Quebec experienced in 1989. They do not eliminate it. The storm is in its main phase. The BES has been negative 45 nanoteslas for 2 hours and 20 minutes. The magnetosphere is compressed. The ring current is intensifying. The geomagnetically induced currents are flowing in grounded conductors across the entire sunlit hemisphere of Earth right now. We will come back to what the grid is doing at this exact moment in Act 8. But first, there is a 6-hour period during this storm that I need to address. A 6-hour window that, if you are watching news coverage right now, you may be hearing described as evidence that the worst is over. It is not. At approximately hour 4 of the main phase, the SWPC monitoring showed something that the duty forecasters noted with cautious relief. The BZ component, which had been sustained at negative 45 nanoteslas since first contact, began to fluctuate upward, not dramatically, not a full reversal to positive values. But the sustained floor of negative 45 began showing intermittent rises to negative 20, negative 15. The KP index, which had been pinned at the maximum value of 9, ticked down to 8. The DST index, plummeting steadily since the storm's main phase began, showed a brief plateau. Media outlets that monitor SWPC data picked up the trend. Several published headlines suggesting the storm was moderating. Social media posts from amateur space weather monitors noted the apparent improvement in the DST trace. A popular science news aggregator ran a story under the headline, "Worst of Solar Storm May Have Passed, Scientists Say." The article was not inaccurate, given the information available at the moment it was written. It was catastrophically premature. The structure of a complex CME is not a single homogeneous cloud. The magnetic cloud that forms the main body of a CME has internal structure. Regions of strongly southward field can be separated by thinner intervals of less organized or even northward field. When Earth's magnetosphere passes through such an interval, the ring current injection briefly decelerates. The DST trace flattens or shows slight recovery. The magnetopause relaxes marginally. Then the next region of strongly southward field arrives. The magnetosphere, which has partially relaxed during the interval, is now encountering another intense southward driver. The reconnection at the dayside magnetopause re-engages. The ring current intensifies again, often more rapidly than during the initial main phase, because the magnetosphere is already in a disturbed state with elevated particle populations from the first main phase. This second intensification is sometimes called the storm recovery interruption. In severe events, it is not a recovery at all. It is a reset to full main phase conditions, or worse. The Parker Solar Probe data, transmitted before the eruption, revealed something in the pre-eruptive magnetic topology that the solar physics team flagged immediately. Evidence that the CME was a compound event. Not a single eruption, but a double eruption, 2 successive CME structures that erupted from the same active region approximately 6 hours apart, and that were observed to interact and merge during their transit through interplanetary space. Interacting CMEs are known to produce enhanced geo-effectiveness compared to single CMEs. When two CMEs merge, the magnetic field structure of the combined event can be more complex and more persistently southward than either component individually. The sheath region between the two ejecta, compressed during the merger, can produce intense BZ fluctuations. The solar physics team flagged this possibility in their initial alert. The operational SWPC advisory included language noting the compound nature of the eruption and the elevated uncertainty in the storm's duration. That language was in the full advisory text. The headline summarizing the advisory did not include it. The apparent moderation at hour 4 was the interval between the first and second magnetic cloud. 3 hours after the moderating headlines ran, the second magnetic cloud arrived. The BZ dropped immediately to -52 nanoteslas. The KP index returned to 9. The DST index, which had partially recovered from its minimum of -390 to -310, resumed its decline. The power companies that had begun the process of returning some protected equipment to service halted the returns and went back to emergency protocols. The 22 million people across the northeastern grid who had been receiving reassurance from the headlines were now in the main phase of the second, stronger event, without the hours of psychological and logistical preparation that had preceded the first. This is the midpoint reversal of this storm, not a reversal of the threat, a reversal of the hope that the threat was passing. The storm is not over. The second magnetic cloud is larger and more intensely organized than the first, and it is going to interact with a magnetosphere that has already been disturbed for 6 hours, a magnetosphere whose ring current is already elevated, whose magnetopause has already been repeatedly breached, whose energetic particle populations are already at storm time levels. The second main phase has begun. The power grid is the vulnerability that receives the most attention in solar storm impact assessments. It is the most visible, the most immediately understood, and the most extensively modeled. But the power grid is not the only system in the path of this storm. There are 6 categories of infrastructure operating under simultaneous stress right now. Understanding all of them, understanding how they interact and how failures in one category amplify vulnerabilities in others, is essential to understanding the full scope of what a G5 event at this level actually means. The first category is satellite operations. There are approximately 10,000 active satellites in orbit around Earth as of 2020. They span a vast range of orbital altitudes, from low Earth orbit beginning at approximately 200 kilometers to geostationary orbit at 35,786 kilometers. Each orbital altitude interacts with the geomagnetic storm differently. Satellites in low Earth orbit experience 2 effects. The first is increased atmospheric drag. During a severe geomagnetic storm, the upper atmosphere, the thermosphere, absorbs energy from the enhanced particle precipitation and expands, extending the effective atmosphere to higher altitudes. Satellites that were orbiting in near vacuum suddenly find themselves moving through a denser medium. The drag slows them, lowering their orbits. If uncorrected, satellites will deorbit faster than intended. During the May 2024 event, SpaceX reported that dozens of Starlink satellites in the lowest operational orbits experienced increased drag and required orbit-raising maneuvers to maintain their intended positions. The total constellation survived because Starlink's design includes onboard propulsion and automated responses to drag anomalies. Not all satellite constellations are as well equipped. The second effect on LEO satellites is charging. The intense energetic electron population that builds up in the magnetosphere during a severe storm, the outer radiation belt, dramatically enhanced during a strong event, can charge satellite surfaces and internal components differentially, producing electrostatic discharges that damage electronics. Several satellite anomalies and losses have been attributed to electrostatic discharge events during historical geomagnetic storms. Geostationary satellites, orbiting in or near the outer radiation belt, face the most severe radiation environment during a major storm. The energetic electrons that fill the outer belt during the storm's main phase penetrate satellite shielding and deposit charge in dielectric materials used in electronics and solar panels. Deep dielectric charging produces delayed discharge events, satellite anomalies that occur hours to days after the storm, as the deposited charge builds to discharge threshold. The GPS constellation operates at medium Earth orbit, approximately 20,200 kilometers. During severe geomagnetic storms, the ionosphere, the charged upper atmosphere that GPS signals pass through on their way to ground receivers, becomes highly disturbed. The electron density variations in the ionospheric plasma introduce errors in the GPS signal propagation that translate to degraded positioning accuracy. During the Halloween storms of 2003, GPS positioning errors in high-latitude regions reached tens of meters, compared to the sub-meter accuracy users normally expect. Modern GPS-dependent applications, precision agriculture, survey, autonomous vehicles, drone operations, air traffic control approaches are calibrated for the normal accuracy range. Errors of tens of meters are not a minor inconvenience. They render some applications operationally unusable. The second category is aviation. Commercial aviation operates global polar routes, great circle routes crossing high latitudes that substantially reduce flight times on trans-Pacific and transatlantic routes. Aircraft on polar routes are exposed to elevated radiation during solar energetic particle events, the radiation storms that accompany major solar flares. Flight crews and passengers receive higher radiation doses than on lower latitude routes. For severe events, the dose rates can approach occupational exposure limits for multiple polar crossings during a single storm. Airlines operating polar routes monitor space weather alerts and divert flights to lower latitudes when radiation storm thresholds are exceeded. Diversions add hours to flight time and significant fuel costs. During the Halloween 2003 storms, numerous polar route diversions occurred, costing airlines millions of dollars in additional fuel and causing widespread schedule disruptions. Additionally, HF high-frequency radio communications, which aviation relies on for long-distance communications, particularly in polar regions where VHF and satellite coverage can be limited, are severely degraded during geomagnetic storms. The ionospheric disturbance that causes GPS accuracy problems also absorbs and scatters HF radio signals, producing blackouts that can affect entire ocean regions simultaneously. The third category is pipeline infrastructure. Pipelines, natural gas, petroleum, water, are long conductive structures buried in the ground or running above it across thousands of kilometers. They are subject to the same Faraday induction effect as power lines. Geomagnetically induced currents flowing through pipeline steel cause electrochemical corrosion at the points where the induced current flows between the metal and the surrounding soil. Pipeline operators monitor cathodic protection systems, sacrificial anodes, and impressed current systems that counteract corrosion. And these systems can be overwhelmed or interfered with during severe GIC events. During the Quebec 1989 event, pipeline operators in Canada and the Nord relay. The trip is automatic. It is the system behaving exactly as designed, protecting its equipment from the abnormal operating condition it is detecting. The loss of reactive power support from the Radisson compensator creates a voltage depression on the northern transmission corridor. The transmission lines, which were already operating at reduced loading as a precautionary measure, show voltage oscillations that the automated protection systems on adjacent equipment interpret as a fault condition. 3 high-voltage transmission lines trip in the next 4 minutes. This is not the same as the 1989 collapse. The 2026 grid has substantially more measurement, monitoring, and automated protective systems than the 1989 grid had. The operators are watching the developments on their SCADA displays in real time. They are taking rapid action. Manual switching operations are being executed to reroute power flows around the tripped lines, but the rate at which the GIC environment is changing, 800 nanoteslas per minute, still rising, means that each protective action taken by the operators is followed within minutes by a new stress on the systems they just reconfigured. At 4:47 a.m., the monitoring system at the Nicolet substation, a critical node in the transmission network serving the Quebec City load center, flags a thermal anomaly in the winding temperature of transformer Unit 7. The transformer's cooling system is operating at maximum capacity. The winding temperature is still rising. The GIC flowing through the transformer's grounded neutral is saturating the core. The saturation produces harmonic currents in the windings. The harmonic currents generate heat. The heat is more than the cooling system was designed to manage. The operators order a manual de-energization of the transformer. With transformer Unit 7 offline at Nicolet, the transmission capacity into the Quebec City area is reduced. The load demand cannot be fully served from the remaining transmission paths. Automatic under-frequency load shedding begins, the system's last resort protective mechanism which intentionally disconnects load in controlled blocks to prevent a full uncontrolled collapse. 1.5 million people in and around Quebec City lose power. This is not a collapse, this is a controlled reduction. The system is managing the situation, not being overwhelmed by it. But the second main phase is still in its early development. The BZ is still -52. The ring current is still intensifying. The rate of change at the magnetometers is still rising. And the morning peak demand, the period between 6 and 9 a.m. when power demand climbs sharply as people wake up, start appliances, turn on lights, and begin the working day, is approximately 90 minutes away. The operators know this. The 90-minute window before peak demand is the operational focus of every decision being made in the control room right now. In the northeastern United States, the scene is similar but less acute. The lower latitude reduces the GIC intensity relative to Quebec, but the US grid has a larger proportion of older unprotected transformers. The PJM interconnection, the regional transmission organization serving approximately 65 million people across 13 states, has activated its emergency protocols. 15 of the largest transmission owners in the PJM footprint are reporting elevated GIC readings on monitored transformers. 2 of those readings are in the range that PJM's contingency guidelines classify as requiring immediate action, either additional cooling or de-energization. The airlines with polar route flights have been diverting since the first main phase began. Approximately 40 commercial flights are currently on diversion to southern routes, adding between 2 and 4 hours to their planned flight times. The airlines' operational control centers are in contact with air traffic control authorities, managing the additional demand on non-polar route corridors. The GPS monitoring systems, operated by the Federal Aviation Administration, are reporting ionospheric disturbance levels in the high-latitude regions that have triggered a degraded operations status for GPS approaches at airports in Alaska, northern Canada, and Iceland. Affected airports have reverted to instrument landing systems and VOR-based approaches for the duration of the degraded GPS period. The transoceanic cable monitoring centers, operated by cable consortia in Madeira, Azores, Greenland, and Newfoundland, are watching their power feed voltage monitors. The Atlantic cables are currently operating within their design parameters, but the margins are narrower than normal. The engineering staff at the monitoring centers are in direct contact with their counterparts at the cable manufacturers to understand the design limits more precisely. At 6:15 a.m., peak demand begins arriving. The combination of reduced transmission capacity, transformer thermal management constraints, and elevated GIC level S on key equipment means that the reserves available to serve the rising demand are substantially below the normal planning margin. Grid operators across the northeastern region are making the decision that no grid operator ever wants to make: controlled, targeted load shedding to protect the integrity of the transmission system. Rolling blackouts begin in a sequence of 15-minute blocks across regions of New England, Ontario, and Quebec. The rolling nature of the blackouts, carefully choreographed to prevent any single area from losing power for extended periods, is a testament to the skill and preparation of the grid operators. The situation is being managed. The catastrophic uncontrolled cascade that the Quebec 1989 event represented is not happening because the grid is better instrumented, better monitored, and better operated than it was in 1989. But 60 million people across the northeastern grid are in rotating blackouts, and Transformer Unit 7 at the Nicolet substation is still running hot. The information that tells you what this storm is doing right now, not what it did 6 hours ago, not what the summary headlines say, but what is actually happening to the magnetosphere and the grid at this moment, is publicly available. All of it, free, updated in real time, no subscription required. The starting point is the NOAA Space Weather Prediction Center at swpc.noaa.gov. The homepage has a dashboard showing current space weather conditions, including the current KP index, the current GOES X-ray flux for solar flare monitoring, and current geomagnetic storm alert levels. The dashboard updates continuously. It is the operational face of the US government's space weather monitoring system. The most important page on the SWPC site for understanding the current storm in real time is the Real-Time Solar Wind page. This page displays the data stream from the DSCOVR satellite at L1 in near real time, typically with a latency of under 1 minute. The parameters displayed include solar wind speed in kilometers per second, proton density, and most critically, the magnetic field components, including BZs. When you load this page and the BZ trace is running below zero, especially far below zero, at values more negative than -10 nanoteslas, the storm's main phase is in progress. The more negative the value, and the longer it has been sustained at negative values, the more energy has been coupled from the solar wind into the magnetosphere. The site also provides the current DST index, which measures the global intensity of the ring current. The DST is updated hourly. A value more negative than -50 nanoteslas indicates a moderate storm. More negative than -100 indicates a severe storm. More negative than -200 indicates an extreme event. During the current storm's first main phase, DST reached approximately -390. The recovery was partial. The second main phase is now driving it lower. The second essential resource is Space Weather Live at spaceweatherlive.com, a community-operated real-time space weather monitoring platform that aggregates data from multiple official sources and presents it in formats designed for non-specialist use. Space Weather Live provides current KP values updated every 3 hours, real-time aurora forecast maps showing where auroras are likely visible at your latitude, current DSCOVR solar wind data, and a live geomagnetic storm alert system. The aurora forecast maps deserve specific attention. During a G5 event of this intensity, auroras are visible at latitudes as far south as 45 degrees, roughly the latitude of Minneapolis, Montreal, or Milan. At the peak of this storm's second main phase, aurora may be visible as far south as 35 degrees, the latitude of Los Angeles, Memphis, and Madrid, under optimal viewing conditions. If you are in this latitude band and have clear skies, the aurora is likely visible to the naked eye right now, even in areas with moderate light pollution. The aurora is beautiful, but it is also the visible expression of the same process that is driving GICs into grid infrastructure. The light in the sky is energy that did not stay in the solar wind. It entered the magnetosphere. It is being deposited in the upper atmosphere. It is flowing in the ionosphere above you. The same dynamics that paint the sky green and red are driving DC currents through transformers 200 kilometers away. The third resource is the Intermagnet Magnetometer Network at intermagnet.org. Intermagnet operates a global network of geomagnetic observatories that measure the Earth's magnetic field at their locations with 1-minute time resolution. During a major geomagnetic storm, the rapid variations in the horizontal field component at high-latitude observatories directly indicate the GIC intensity in nearby power infrastructure. If you see the horizontal component varying by hundreds of nanoteslas per minute at a high-latitude observatory, GICs in that region's GRID are likely at levels that exceed normal operational parameters. The stations most relevant for monitoring the current storm's impact on North American infrastructure are the Minnook, Alberta station, the Ottawa, Ontario station, and the Newport, Washington station for the US Northwest. All three are providing data in real time. The fourth resource is the GOES satellite data at goes.noaa.gov. NOAA operates the GOES geostationary weather satellites, which also carry instruments for monitoring energetic particle flux and X-ray flux from solar activity. The GOES energetic particle data is relevant for aviation radiation monitoring and satellite health. If the proton flux data on the GOES particle monitor shows elevated readings in the greater than 100 MeV channel, radiation levels at polar aviation altitudes are above normal flight crew exposure guidelines. The fifth resource is the specific to this event, the NASA Parker Solar Probe data transmission. The data from the probe's pre-eruption pass has been partially released to the community through NASA's Solar Data Analysis Center. Researchers accessing this data in the hours since the eruption have been posting preliminary analyses to social media and the scientific preprint server Arxiv. The specific finding that the solar physics team flagged, the evidence for a compound double eruption, is visible in the plasma and field measurements from the probe's closest approach. The double-lobed structure of the pre-eruptive flux rope is apparent in the magnetic field vectors measured within 6 million kilometers of the solar surface. This is the closest range measurement of a CME precursor ever made, and it is providing the solar physics community with data of a quality that will be analyzed for years. But for the purpose of understanding the current storm in real time, the key indicator on every available data platform is pointing in the same direction. The second main phase is stronger than the first. It has not yet reached its minimum DST. The BZ is still negative. The grid operators are managing, but managing a G5 event at this intensity in the middle of a morning peak demand period, with the second main phase beginning after the false recovery that prompted partial restoration of protective switching, is operating at the extreme edge of what the system's planning scenarios contemplate. The edge is narrow right now. Watch the BZ, watch the DST, watch for BZ approaching zero from below. A sustained move towards zero means the main phase is ending and the recovery is beginning. That is the signal that the worst of the electromagnetic stress on the grid is over. Until that signal appears, the operational environment for every affected system remains at maximum stress. In 1831, Michael Faraday discovered electromagnetic induction, the physical principle that a changing magnetic field produces an electrical current in a conductor placed within it. Faraday's discovery was the foundation of every electrical generator, every transformer, every motor ever built. The industrial civilization of the last 2 centuries runs on the practical applications of his insight. The power that flows from the dam to your house is produced by electromagnetic induction. The transformer that steps that power down to a voltage your appliances can use is operating on Faraday's principle. The same principle that makes civilization possible is the mechanism by which a solar storm threatens it. The geomagnetically induced current that flows into a transformer's grounded neutral during a severe geomagnetic storm is Faraday induction operating at planetary scale, with the Earth's magnetic field as the conductor and the solar wind as the source of the changing field. The transformer was designed for the induction it produces internally, by design, under controlled conditions. It was not designed for the induction imposed on it from outside, by a star 150 million kilometers away. This is not a design failure. The engineers who built the grid did not know, when most of it was designed and installed, that it was vulnerable to this external electromagnetic input. The space weather impact on power infrastructure was not well understood until well after most of the current grid was built. The vulnerability was discovered through hard experience. The Quebec 1989 collapse was the event that put the issue unambiguously on the radar of the power industry and the government agencies that oversee it. The understanding has been accumulating since 1989. The vulnerability has been progressively better characterized. Mitigation measures have been developed and deployed. The grid is less vulnerable than it was in 1989. It is not invulnerable. The storm, currently in its second main phase, is beyond the range of the historical data on which current vulnerability assessments and mitigation standards are based. It is an event in the tail of the distribution, not unprecedented in the geological record, which carries evidence of Carrington-scale events occurring every few centuries, but unprecedented in the modern instrumental record of geomagnetic monitoring. What do you do with this information? The answer has two components, the immediate and the durable. The immediate response to a G5 geomagnetic storm event is simpler than most people realize. Power outages during the storm are likely in high-latitude regions and possible in mid-latitude regions. The outages may be rolling and controlled as grid operators manage the situation, or they may be uncontrolled if the GIC stress exceeds the grid's management capacity. Either way, the practical preparation for power outage is the same preparation that emergency management agencies recommend for any power disruption. Water stored for drinking and sanitation, food that does not require refrigeration or cooking, medications maintained with adequate supply, battery-powered lighting and communication, and a battery or hand-crank radio for receiving emergency information. The specific addition for a solar storm scenario is awareness of the GPS disruption. If you are planning any activity that depends on GPS navigation, driving in unfamiliar areas, using location-based services, operating any precision positioning equipment, be aware that GPS accuracy may be severely degraded during the storm's main phase and the subsequent recovery period, which can last 24 to 48 hours. Aviation passengers in transit during the storm should be aware that polar route diversions may add hours to their flights and that HF radio communications are disrupted, which may affect the information available to flight crews in some areas. For anyone with medical devices that depend on power or on cellular network connectivity, implanted defibrillators with remote monitoring, home oxygen concentrators, insulin pumps with connected features, the storm period is a time to have backup plans confirmed and backup power resources available. None of this is extreme or unusual preparation. It is the same level of readiness that thoughtful people maintain for any severe weather event. The durable response is different. The durable response is the one that, if enough people in enough positions of responsibility execute it, reduces the vulnerability of the infrastructure to the next event of this scale. Let me give that durable response a concrete shape, because abstract arguments about infrastructure investment are less actionable than specific proposals. The first specific proposal is the L5 monitoring spacecraft. The scientific and technical case for placing a space weather monitoring satellite at the L5 Lagrange point, which trails Earth in its orbit by 60 degrees, providing a side-on view of the Sun-Earth system, has been documented in multiple government and academic studies. An L5 satellite would provide early warning of CME eruptions approximately 2 to 3 days before they arrive at Earth, and would allow continuous monitoring of the CME's magnetic field structure as it evolves during transit. This monitoring would constrain the BZ forecast uncertainty that currently makes the 15-minute warning at L1 the primary operational input. The European Space Agency has a mission called Vigil in Development, planned for launch in the early 2030 OS, that would provide exactly this capability. NASA and NOAA have conducted feasibility studies for L5 missions, but have not yet secured funding for a dedicated US asset. The cost of an L5 space weather mission is estimated at several $100 million, a fraction of the economic impact of a single major grid failure event. The second specific proposal is the mandatory neutral blocking capacitor program. GIC blocking devices for high-voltage transformer neutral connections exist, have been tested, and are commercially available. Their installation on the most vulnerable transformers in the North American grid has been proceeding voluntarily but slowly. A mandatory regulatory program requiring the highest-risk transformers to be retrofitted within a defined timeline would accelerate the implementation from decades to years. The third specific proposal is a strategic transformer reserve. The Department of Energy has studied this option. A government-held reserve of spare EHV transformers sized to cover the most likely failure scenarios from a severe geomagnetic event, positioned regionally for rapid deployment, would dramatically reduce the recovery timeline from any transformer failures that do occur despite protective measures. The fourth proposal is the inclusion of space weather impacts in the standard design requirements for undersea telecommunications cables. The next generation of cable designs, which will be laid in the coming decade to meet growing international bandwidth demand, can incorporate protection against GIC-induced voltage stress, their power feed circuits, at relatively modest additional cost, if the design requirement is established before the engineering is finalized. None of these proposals requires novel technology. All of them have been studied and documented by credible institutions. All of them face the same obstacle: priority. The competition for budget and attention against other risks, other needs, other political priorities. Every major space weather event that occurs without causing a catastrophic infrastructure failure is simultaneously a near miss and an opportunity. A near miss because the event could have been worse. An opportunity because the event provides data, demonstrates the reality of the threat, and creates a window of attention and will to act. The storm, currently in its second main phase, is the largest geomagnetic event in the modern instrumental record. The systems built to manage it are being tested at the edge of their design envelope. And the lesson that emerges from this storm, whether the grid manages it fully or partially, whether the cascades remain controlled or extend further than the operators can contain, is the same lesson that the space weather community has been articulating since 1989. The standards and mitigation programs that have been developed in that time represent genuine progress, but the pace of mitigation has been constrained by cost, by the long lifetimes of existing equipment that makes replacement slow, and by the political and regulatory challenges of investing in protection against low-frequency but high-consequence events. There is a concept in risk management called the risk normalization gap. It describes the tendency of institutions and societies to calibrate their protective investment to the risk profile of the events they have recently experienced, rather than to the full probability distribution of events that could occur. When decades pass without a catastrophic space weather event, the investment in protection tends to drift toward the lower end of what the risk analysis justifies. The organizational memory of the last significant event fades. The budget pressure builds from other directions. The May 2024 event temporarily reversed this drift. The current event, which has already exceeded May 2024 in every measured dimension, is creating a moment of clarity about what the risk actually is. Not the theoretical risk described in policy documents, the operational risk that the duty forecasters in Boulder are managing right now. That moment of clarity is the resource that matters. What happens in the weeks and months after this storm, whether the institutional memory is acted upon or allowed to fade as the aurora fades, will determine how ready civilization is for the next event of this scale. Solar cycle 25 is still near its maximum. The active region that produced the current eruption is still on the solar disk. It will rotate out of view in the coming days and return in approximately 2 weeks. Whether it produces another major eruption on its second pass, no one can say. What can be said with certainty is that the conditions that produced the current event will recur. They always have. The Carrington event was not a statistical anomaly. It was an extreme expression of a process built into the sun's magnetic cycle. It happened once in the observational era. It will happen again. The question this storm makes urgent is not whether we can prevent the sun from producing extreme events. We cannot. The question is whether we choose to build our civilization's electromagnetic infrastructure in a way that can survive them. The space weather research community has been making the case for an L5 monitoring spacecraft, which would provide hours rather than minutes of warning for incoming CMEs for decades. The scientific case for it is unambiguous. The engineering is well understood. The cost is modest relative to the infrastructure it would help protect. The political will to fund it has been intermittent. The undersea cable vulnerability is largely uncharacterized in current space weather impact assessments and has not yet been incorporated into the planning frameworks of the telecommunications industry. These are solvable problems. They have known solutions. The obstacles are not scientific or engineering obstacles. They are resource and priority obstacles. Every major space weather event that occurs without causing a catastrophic infrastructure failure is simultaneously a near miss and an opportunity. A near miss because the event could have been worse. An opportunity because the event provides data, demonstrates the reality of the threat, and creates a window of attention and will to act. The storm, currently in its second main phase, is the largest geomagnetic event in the modern instrumental record. The systems built to manage it are being tested at the edge of their design envelope. And the lesson that emerges from this storm, whether the grid manages it fully or partially, whether the cascades remain controlled or extend further than the operators can contain, is the same lesson that the space weather community has been articulating since 1989. The Sun is not a stable star. It has a cycle, and that cycle produces, with regularity, events that are capable of affecting every electromagnetic system on this planet simultaneously. We have built an electromagnetic civilization. We have extended every critical function of modern life, power, communication, transportation, finance, agriculture, medicine, across electromagnetic infrastructure that spans the planet. We have done this without fully incorporating the behavior of the star at the center of our solar system into the design constraints for that infrastructure. The Carrington event of 1859 happened before that infrastructure existed. The world survived it without consequence because the telegraph was a 19th century technology with 19th century resilience. The next Carrington event will happen against the backdrop of a civilization that did not exist in 1859, a civilization that runs on Faraday's principle, a civilization that lives inside the electromagnetic environment that the Sun controls. The storm currently in its second main phase is not the Carrington event, but it is the most powerful event the modern instrumental era has recorded. And the question it poses, not as a rhetorical device, but as a genuine and immediate policy question, is whether the civilization that built itself on electromagnetic infrastructure has done enough to make that infrastructure resilient to the star it orbits. The auroras are visible right now from latitudes where they have never been seen in living memory. The grid operators in Montreal and New York and Chicago are working through their protocols with skill and urgency. The DSCOVR satellite is still reading negative BZ values. The second main phase has not yet reached its minimum. The window is still open, both in the operational sense of the storm still being in progress and in the longer institutional sense of the decisions that this event makes urgent. Use the data, understand the mechanism, prepare for the immediate, and remember when the auroras fade and the grid stabilizes and the all-clear is issued that the Sun did this once before, that it will do it again, and that the only variable between a cosmic event and a civilizational catastrophe is the resilience of the infrastructure in between. The transformer at Nicolay is still running hot. The BZ is still negative, and somewhere in the corona of the Sun, the next active region is building. If this kind of deep, mechanism-level analysis of space weather events is useful to you, the kind that explains what BZ means and why it matters, that walks you through the grid physics and the satellite vulnerabilities and the 15-minute warning window, subscribe now and turn on notifications. In the next video in this series, we go inside the Space Weather Prediction Center in Boulder, Colorado, how the duty forecasters read the data, what the monitoring screens look like during a G5 event, the specific decision points that separate a managed storm from an unmanaged cascade, and the one development currently in the planning stages at NASA and ESA that could change the 15-minute warning window into something that actually allows infrastructure protection to happen. In the comments below, I want to know where you are and what you are seeing. Are the auroras visible from your location right now? Has your power been affected? And more fundamentally, after understanding the mechanism, the BZ, the GIC, the transformer vulnerability, the 15-minute window, what do you think needs to change? Not the most frightening answer, not the most reassuring answer, the most accurate answer given what the data shows. The storm is still active, the data is still updating, the Sun is watching,